So, hello everyone, I'm Himanshu Vasnani from Department of Mechanical Engineering and I'm here with you to discuss on the subject Material Science. The subject code is ME207, unit number 3, lecture number 20 in the series, and the topics are radiation parameters and surface finish after heat treatment. So let's start with these topics for today. Our learning objective for today is to provide the students with a basic understanding of radiation parameters, surface finish after heat treatment. And today's learning outcome will be students will have learned the basics of radiation parameters, surface finish after heat treatment, and also the students have understood various types of radiation parameters. So let's start with the topic today. To remove the no, sorry surface finish after heat treatment, but to remove the defects caused due to faulty heat treatment processes. Various faulty heat treatments that we have discussed in our earlier classes like oxidation, burning, and various kinds of overheating. Uh, you can say some kind of you can say unwanted salt bath. So these kind of faulty heat treatments which we discussed in the previous classes also. So to remove those defects that are caused due to the faulty heat treatment processes, certain finishing operations are carried out prior to use of assembly of the same. The few of these are like the first one is acid pickling. Okay. Now if the heat treatment is not performed in a controlled gas atmosphere, the oxide or the scale layer is formed on the surface of heat treated component. Okay, if the heat treatment is not performed in a controlled gas atmosphere, okay, then there a layer or you can say a scale layer is formed on the surface of heat treated component. So for this, we do descaling. So descaling is done by acid pickling. Okay, either by the mechanical circulation or by direct dissolution of the component in an acid bath. Okay, to avoid that scale layer, we do descaling. Okay, and equate the reaction for the acid bath is FeO plus H2SO4 gives FeSO4 plus H2O. So for the above purpose, 8 to 12% H2SO4 or 20% HCl as it is taken, the acid bath is usually used at 50 to 70 degree temperature, and the components removed from the pickling bath are thoroughly cleaned and steamed, and they are neutralized in a weak alkaline bath for about 5 to 10 minutes. So finally, they are rinsed by warm water. So in this way, you go for acid pickling. The second method is the sandblasting. Okay, after this acid pickling, we go for sandblasting. A jet of compressed air carrying sand composed of dry, sharp quartz grains of 1 to 12 mm is directed against the surface to be cleaned after heat treatment. Okay, you have a jet of compressed air having all such you can say components of a particular size of 1 to 12 mm, and then this process is provides fine surface and quite useful for large areas to be cleaned. So in this process a good amount of dust is generated which requires precautions for operators, obviously, because some breathing problem may occur because it has dust, sorry, it has sand, it has some sharp edge grains of maybe some quartz. So when you are directing this compressed air on a particular surface, then obviously it may spread in the nearby area. So the operators or should be you can say take some precautions to protect themselves from such kind of you can say atmosphere. Okay, so to avoid inhalation of dust, protective measures are essential like the one you can see in the diagram. The operator is wearing a helmet. Okay, the helmets to protect himself from such kind of uh, you can say the such kind of sand in the atmosphere. So dust, obviously dust in the atmosphere. So to avoid inhalation, operators are provided with respirators and sand blast hoods. Obviously, you can see the diagram. There is another method of surface cleaning called as short blasting. Okay, So now sandblasting again. The surface cleaning is performed by centrifugal action of the abrasive material like iron shots instead of sand and blowing with pneumatic pressure. Okay, now it is using iron shots instead of sand. Earlier we were using this with pneumatic pressure, so it also produces cold case hardening of surface, increasing the fatigue resistance of the articles. So it is there than decreasing an alkaline degreasing and alkaline detergent cleaning. So when treated in salt bath, a number of components have salt deposits. Okay, these can be removed by soaking the components in a boiling water. So the tools tempered and quenched in oil have a greasy material deposit on the surface. So these are usually cleaned by 10% biovolume soda ash solution at 80 to 90 degrees centigrade or 3% solution of caustic soda. Now they are cleaning that, you can say, greasy material on the surface. So both salt and oil deposits can be cleaned by immersing the components in a tank containing boiling soda solution and then washing in water. This is operation also known as vat or soap cleaning. So you can see the tanks on the right hand side in the diagram. Okay, so here you can understand that how they are cleaned. Okay, now straightening. Now during heat treatment, certain tools, machines, parts get distorted or warped. Okay, this is also you can say defect that we discussed yesterday, distortion and warping. So to bring back to the original shape, then we go for straightening is carried out. Okay, the straightening of roll stock is usually done by roll straighteners or hydraulic straightening presses. So they usually are used for straightening the you can say workpiece or machine parts or tools, whatever the we have done the heat treatment. Okay, so we have finished with that. Now we are starting with the radiation parameters. So measurement of high temperatures and parameters. In the heat treatment, we have studied about various processes like annealing, normalizing, hardening, tempering, nitriding, cyaniding, uh, uh, carburizing. So they were having a particular temperature on which these processes were done. And in the iron phase diagram also, you have seen that there was in the on the vertical axis, the temperature was around 1600 degrees centigrade. That was the limit because the temperature that we last studied was 1538 degrees centigrade on this diagram. So, if we go beyond that temperature, then what should we do? So now the physics of measurement of very high temperature above 1600 degrees centigrade is called as pyrometry. It is called as pyrometry. So the devices used for such high temperatures are called pyrometers. Now we are going beyond 600 degrees centigrade. Okay, so beyond 1600 degrees centigrade. So we call this system is called as pyrometry of measure. Okay, pyrometry. The physics of measurement is called as pyrometry, and the devices that are used for such high temperatures are called as pyrometers. So some of these pyrometers are used thermal radiations from hot bodies which depend for black bodies only on temperatures of body, and hence they are known as radiation pyrometers. Okay, they are known as radiation pyrometers. You can see in the diagram also there is the arrangement of Fairy's total radiation parameter. We will be discussing this in the coming slides for your help. Ah, two different types of radiation parameters are used for the measurement of high temperature. Like the first one is total radiation parameter. Now, in this total radiation parameters, the types of instruments, the total energy of the radiation emitted by the body under test is measured. Okay, it is measured, and the temperature is obtained by applying the Stephen's law, assuming that the body is black. Okay, assuming that the body is black, we go for this total radiation parameters. And the second is the optical or spectral parameters. Okay. In this, then these are based on the Gyan's distribution law, where the intensity of radiation of a certain wavelength emitted by the body is compared with that of the radiation of same wavelength emitted by the standard body at the known temperature. I repeat, you can understand this that this or spectral parameters, these are based on the Wien's distribution law. And how they do, the intensity of radiation of a certain wavelength, the intensity of radiation of a certain wavelength emitted by the body is compared with that of the radiation of same wavelength emitted by the standard body, emitted by a standard body at a known temperature. Okay, by the standard body at a known temperature. So the temperature of the body is deducted from Wien's distribution law, or more accurately from Planck's law. Okay, so these are the two you can say types of radiation parameters. So now we discuss about Ferry's total radiation parameters. Okay, so this Ferry in 1902 devised the first radiation parameter as shown in this figure. You can see on the right hand side. So it is virtually a reflecting telescope with a concave mirror M. Okay, you can see the capital M written there in the diagram of a nickel plated copper or gold coated glass. Okay, it has a nickel plated copper or a gold coated glass with an IE. You can see an eyepiece E fitted coaxially with a hole in its center. Okay, now it is fitted with a hole in the center. Now mirror can be moved by the rack and pin arrangement. Okay, a metal disc with you can say with its front face blackened. Now you are taking a metal disc and its front faces blackened is placed at the focus of the mirror and receives the radiation from the body whose temperature is to be measured after reflection at the mirror. I repeat about the metal disc. A metal disc with its front face blackened. Now you have blackened the front face of the metal plate. Okay, of the metal disc. Sorry, of the metal disc you have blackened it. It is placed at the focus of the mirror and receives the radiation from the body whose temperature is to be measured after reflection at the mirror. Now two plane like semicircular mirrors M. You can see the small m written on the in the diagram. Okay, in the center. Small m inclined to each other at about 5 degrees. Okay, with an opening of about 1.5 mm. Okay, with an opening of about 1.5 mm at the center are placed in front hole in the mirror. Any direct radiation is prevented from falling upon the disc by placing a suitable enclosure around it. So at the back of the disc is attached to one junction of thermocouple whose colder junction is shielded from direct radiation by means of a tongti. A millivoltmeter is connected from the leads of the thermocouple. This is just an arrangement. Okay, this is the arrangement, the working of the parameter. Now the radiations from the hot body, okay, and the test falls on the concave mirror M, capital M. You can see capital M in the diagram, which focuses it on the opening between small m. Now this concave mirror is focusing that on the opening between small m. Okay, m and m. Now the opening is seen with the help of an eyepiece E, capital E, through the hole in M, in capital M. Okay, you are the opening is seen with the help of an eyepiece capital E. You can see in the diagram through the hole in capital M. Now the position of the mirror capital E through capital M is so adjusted that the appearance through the eyepiece is shown in this figure. You can see in the figure 10.16, then in the A figure, you can see how the appearance of through the eyepiece look like. Now clearly the radiation which is properly focused on the opening between small m, then small m falls on S. You can see the letter S written on the in the diagram. Okay, which is therefore heated. Now the heating is there on the small in the capital S. Okay, it is therefore heated and produces a thermo EMF reading in the millivoltmeter is recorded. The readings are recorded in the millivoltmeter. The calculation of the temperature. If capital V is the reading in of millivolt meter, okay, if capital V is the reading of millivolt meter, then capital V is equals to A into e raised to the power 4 minus t raised to the power minus t naught e raised to the power 4. So here capital T is the absolute temperature of the source. T naught is the absolute temperature of the strip, and small a is the constant, which is not the same as Stephen's constant. So one can determine the value of a by obtaining the values of capital V corresponding to a known temperature T. So if T is very much higher than T naught, then capital V is equals to A into T raised to the power 4. The instrument is calibrated by receiving radiations from the black body maintained at known different temperatures. The temperature measured from a standard thermocouple and the corresponding readings of a millivoltmeter are recorded. So a calibration curve is plotted between logarithm of capital V versus logarithm of capital T, which is a straight line. Okay, and the millivoltmeter may also be directly calibrated in degrees. This is how you do the calculation of temperature in this. Now, modification for temperature of very high modification of measurement. Okay, modification of measurement of very high temperature. Now to measure the temperature above 1400 degrees centigrade, a rapidly rotating sector that is shown in this figure in the right hand side is interposed between the hot body and the pyrometer. Now, if beta is the angle of the sector, then it will follow only a fraction, that is beta upon 360. Okay, the fraction is called as beta upon 360 of the incident radiation to enter the parameter. Now, the parameter indicates a temperature which is less than the true temperature of the body. The modification for temperature of very high temperature, you can go again. Then, since the radiation is proportional to the fourth power of the absolute temperature. Therefore, if if capital T be the true temperature of the body and T1 that indicated by the parameter. Now capital T is the true temperature of the body and T1 is indicated by the parameter. Then we can write that T1 raised to the power 4 is equals to theta upon 360 into T raised to the power 4. Now here capital T is the true temperature of the body and capital T1 is indicated by the pyrometer. So capital T will be is equals to T1 into 360 by theta whole power 1 upon 4. And this T, the black body temperature of the body, can be easily obtained by this. Okay, this formula. Okay, the modification of or measurement of very high temperature. So to measure about this, you can say the advantages and drawback of this instrument. Okay, now the advantage is the most important advantage of the total radiation parameter is that it can be easily adapted for a continuous recording of temperature. For example, the roof of an open heart. Okay, so this is the advantage that it can be easily adapted for a continuous recording of temperature. And the drawbacks is that is not suitable for the measurement of temperature of smaller bodies whose heat image is likely to be too small to cover the whole of the disk. Now calibration, calibrated in the manner I described above, its utility is confined to the limited range that is 800 degrees centigrade to 1600 degrees centigrade. We have a limit. Then the readings of the apparatus, while theoretically quite independent of the distance, quite independent of the distance from the hot body, are not really so in actual practice. So due to conduction along the wires of thermocouple, the Stefan's fourth power law is not strictly applicable. Okay, the power of temperature capital T varies from 3.8 to 4.2. Now the optical parameters. Okay, now we're discussing about optical parameters. Now two types of optical parameters are commonly used. The first is the disappearing filament parameter and second is the polarizing parameter. Okay, you can see the diagram of disappearing filament parameter. Okay, there you can see the eye and the other arrangements and I will discuss you in the coming slides. So disappearing filament parameter. Now a modified form of the disappearing filament due to the Hall-Bourne and Forsey is shown in this diagram. Now it consists of a telescopic objective, capital L, and I now the you can see the capital E is there shown easily. Okay. Now the crosswire of telescope are replaced by the tungsten filament of a highly evacuated electric lamp, flanked by two limiting diagrams, capital D1 and capital D2. You can see in the diagram there. The filament is heated by the current from the 2-volt battery and is temperature controlled by adjusting the current with the help of the rheostat capital R. Now the telescope is directed towards the hot body whose temperature is to be determined. So by adjusting the position of the telescope, position of the objective of telescope, capital L. Okay, by adjusting the position of the objective of the telescope L, an image of the black body is focused on the filament F. Okay, you can see that image on of the black body is focused on the filament capital F. Now, the temperature of the filament is adjusted by means of the rheostat capital R until the filament F disappears against the image of the black body. Now, when the brightness of the filament capital F, when the when the brightness of the filament F and that of the black body have been exactly matched, the reading of the emitter A is noted. You can see the emitter A in the diagram. Okay, their reading is noted at that point. Okay, when the brightness of the filament F and then that of the black body have exactly matched. You note down the reading. The calculation of the temperature. So when the brightness of the black body and that of the filament F are same, then the emissive powers will be equal. So evidently the temperature of the black body will be equal to that of the filament. The temperature of the filament, and that is of the black body, you can calculate from the relation I is equals to A plus small bt is equals to Ct square. So here I is the current flowing through the filament. A, B, and C are constants. These constants are determined by calibrating the instrument against known temperature. So this type of parameter can normally measure temperatures from 700 degrees centigrade to 1500 degrees centigrade. This is the limit. The range can be extended to 2700 degrees centigrade. Well, normally they can measure 700 degree to 1500 degrees centigrade, but the range can be okay. Understand the 700 to 1500 degrees centigrade only, but this range can be extended to 2700 degrees centigrade by rotating sector. So see how the temperature has increased to such a limit. The advantage is that it is portable, it can be used to determine the temperature of even small bodies. Since the tip of the filament can be matched with any part of the image seen through the telescope, it can be easily constructed and this makes it highly precise and accurate. And the theory underlying it is relatively less affected by the departure of the body from a perfectly black body, so that the corrections involved are comparatively much smaller. Okay, now drawbacks are it requires some wavelength in the visible part of the spectrum for its working and cannot, and therefore be used for measuring temperatures of body which are not actually glowing. So furthermore, this is some uncertainty as to the actual wavelength. Okay, there is some uncertainty as to the actual wavelength of the radiation used. This is a drawback that there is some uncertainty as to the actual wavelength of the radiation used. Then the polarizing optical parameter. Okay. Now, when devised in 1901, an optical parameter in which a ray was of a in which a ray of a particular color from a hot body is compared with the ray of the same color from a standard electric lamp by means of a polarizing device. Now, this is the you can say kind of thought that came the instrument is more of a polarizing parameter, so its essential part are shown in this figure. You can easily see that in the figure how it's there. Now radiation starting from the hot body after passing through the hole O1. Okay, you can see the O1 on the upper side of the diagram. Fall on a calcite prism P. Okay, the P is there, the prism is shown. Now calcite being doubly refracted crystal breaks the beam into two components polarized at right angles to each other. Okay, now these beams pass through the big prism B, capital B. Through the biprism. Okay, now these beams uh, pass through a bioprism B, which bends them in such a way. Okay, this B bioprism, which bends them in such a way that the horizontal component passes through a limiting diaphragm capital D. Now you can see the capital D diagram, how it is passing through. Where the vertical component is cut off, you can see the vertical component. Okay, the arrows are, you can see the arrows shown in the paragraph are matching with the arrows in the diagram. Similarly, a radiation beam from a standard body at a steady temperature. Similarly, a radiation beam from the standard body at a steady temperature is allowed to pass through the system. But in this case, the vertical component passes and the horizontal component is cut off. Okay, these two mutually perpendicular beams emerging from D pass through the Nicol prism capital N. You can see the Nicol prism. And then from a red filter F, you can see the filter capital F. The two circular patches of lights are observed when we look through the eyepiece, capital E. You can see the eyepiece, capital E in there. The Nicol prism N is rotated. Okay, in one particular position of N, the light from the hot body transmits fully through N, whereas the light from the standard body is completely cut off. So when the Nicol is rotated by 90 degrees from this position, and then vice versa is happens. From this position, the Nicholson's end is gradually rotated till the two patches of light appear equally bright. That is, the light from both the bodies is transmitted equally through N. Okay, through the N, that is the Nicol prism. The angle through which the Nicol is turned for the purpose is read on a circular scale attached to it. Let it be theta. So if E lambda be the intensity, okay, E lambda be the intensity of radiation after filtration through F from the hot body, and S lambda be the intensity of the radiation of the same color from the standard body, then E lambda upon S lambda is equals to 10 square theta. This is the relation. So let E lambda dash be the intensity of radiation from the second hot body in place of first body, and theta dash be the angle of the rotation of N. Then E lambda dash upon S lambda is equals to 10 square theta dash. So from these two figure, you can say equations, you get that E lambda upon E lambda dash is equals to 10 square theta upon 10 square theta dash. So from means distribution law, we have this equation with you. Okay, that E lambda is equals to A lambda minus raised to the power minus 5 upon E upon minus V theta upon lambda t. Okay, so this relation is there for E lambda and E lambda dash with you. Okay. Now here A and B are constant, capital A and B are constants, and T and T dash are temperatures of hot body, okay, under test and second body respectively. T and T dash are temperatures of the hot body under test and second body. So you can see with this formula you got a ratio of E lambda and E lambda dash, and similarly for the theta, that is 10 square theta upon 10 square theta dash, you got this equation. So if you take log on both sides, you get the equation number 9 that is written on the screen. Okay, so when we have a linear relation between the log tan theta and 1 upon t in the form, then we get the log of tan theta is equal to a plus b upon t. Okay, now here a and b, you can see the small a and b also, these are constant, and what you can obtain them by calculating the parameter against the known temperature. So knowing small a, b and theta, one can easily evaluate the temperature of the given hot body. The normal range of this parameter is from 700 to 1400 degrees centigrade, but the range can be raised to 4000 degrees centigrade. Now it is having more range than the previous parameter by putting an absorption glass in the path of an incident radiation. You can see how this has increased the radiation. Okay, now we are going to the small, you can say, revision of the heat treatment processes that we studied till now for a general idea, so that you can easily understand and find out that the whole all the processes are in you can say are studied by you. Like if you go for the annealing, so annealing involves heating the material to a determined temperature and holding the material at a temperature and cool the material to room temperature slowly. Okay, you can see with the diagram how the annealed metals look like. So they are slightly softer, where hardened materials are difficult to turn. Okay, so the process involves like heating the material at the elevated or predetermined temperature, then holding the material, soaking the at temperature for longer time, and very slowly cooling the material to room temperature. So this is how annealing process is done. Now, the purpose for this annealing heat treatment process is like relieving the internal stresses developed during solidification, matching, forging, rolling, or welding, and to improve or restore ductility and toughness. And the most important thing, enhance machinability, because what happens during the casting, or you can say like these are the some elementary production processes. So during the casting or welding process, even some kind of you can say uh, defects like blowholes or porosity or things, some problems or faults may come. So annealing tries to release those you can say stresses, and then make the work, you can say, workpiece easily under you can say machinable, and hence they enhance the machinability of the workpiece. Then eliminate chemical and non-uniformity, chemical non-uniformities there, than refrain grain size and reduce the gaseous contents in steel. The normalizing process, second process that we studied. So you can see in the diagram there is a normalizing range shown above AC3 line. Okay. So here this normalizing is similar to cooling, except steel is generally cooled in still air. Okay. Now they are cooling in the still air, and the normalizing consists of heating the steel to about 40 to 455 degrees centigrade above critical temperature. You can see that is shown by AC3 or ACM, and holding the proper item and then cooling in still air or slightly agitated air to room temperature. Now, in some special cases, cooling rates can be controlled by the changing air temperature or air volume. So you can see the diagram showing this. Normalized treatment is frequently applied to steel in order to achieve any one of these objectives, like to refine grain structure or to obtain uniform structure or to decrease residual stresses or to improve machinability. Okay, so this is the reason why we go for a normalizing process. Okay, now hardening. Now hardening and hardness are two different things. Okay, one is the process of heat treatment, that is hardening, and the other is an extrinsic property of a material. Like hardening is a heat treatment process in which steel is rapidly cooled from austenizing temperature. So as a result of hardening, the hardness and the wear resistance of steel is improved. Now this is the effect of hardening. The hardness and the wear resistance of the steel is improved. Okay, so this in this way hardening process is helpful, and that is why we go for this kind of heat treatment. And hardening treatment generally consists of heating to hardening temperature, holding at that temperature, followed by rapid cooling, such as quenching in oil or water or salt bath. Whatever is the based upon the past experiences, whatever you want to do, the quenching in, you can use that. Now, the high hardness developed in this process is due to the phase transformation accompanying rapid cooling. Rapid cooling results in the formation of austenite at considerably low temperatures into non-equilibrium products. The hardening temperature depends on chemical composition. For plain carbon steels, it depends on the carbon content alone. Hypoelectric steels are heated to about 30 to 50 degrees centigrade above the upper critical temperature that we have discussed previously also about hypoelectric steels, how we you can say process them. Whereas this electroid or hypoelectric steels are heated to about 30 to 50 degrees above lower critical temperature. Okay. Now the ferrite and pearlite transform to austenite at hardening temperatures for hypoelectric steels, and this austenite transforms to martensite on rapid quenching from hardening temperature. So the presence of martensite accounts for high hardness of a quenched steel. This is how hardening is. So the main purpose of hardening steel to steel is to develop high hardness. That is the purpose. Okay, this enables tool steel to cut other metals. That is why we go for this process. So high hardness developed by this process also improves wear resistance. So gears, shaft, bearings, these are the examples for on which the hardening process is done. And tensile strength and yield strength are improved considerably hardening structural steels. Because of rapid cooling, so high internal stresses are developed in the hardened steels, and hence steels are generally brittle. So hardening is generally followed by another treatment called as tempering. Okay, now you have listened that there was an internal stress. So this tempering process, it reduces the internal stresses, which makes the hardened steel relatively stable. Okay, now tempering. Now hardened steel are so brittle that even a small impact will cause fracture. Okay, the brittleness is too much after tempering. After After hardening process, the brittleness is so much that the hardened steels are so brittle that even a small impact will cause fracture. So toughness of steel can be improved by tempering. However, there is a small reduction in strength and hardness. Okay. Now, tempering is a subcritical heat treatment process which is used to improve the toughness of the hardened steel. So, tempering consists of reheating of hardened steel to a temperature below the lower critical temperature and is held for a time and then slowly cooled in air to room temperature. Okay. Now, at tempering temperature, these carbon atoms they are there. They are diffused out and form fine cementite and softer ferrite structure left behind. So the structure of tempered steel consists of ferrite and fine cementite. You can see the diagram tempered microstructure of that there. There is a tougher microstructure. So thus, tempering allows to precipitate carbon as a very fine carbide and allows the microstructure to return to BCC. The temperatures are related to the function of the parts. So cutting tools are tempered between 230 degrees to 300 degrees centigrade. And if greater ductility and toughness are desired, okay, if you want greater ductility and toughness, so as in case of shafts and high strength bolts, the steel is tempered to a range of 300 to 600 degrees centigrade. So these are again some applications of that. Now tempering temperatures are usually identified by the color. You can see the color, tempering colors of steel at different temperatures, how the different colors are formed in tempering. So tempering temperatures of tools and shafts with along with temper colors that are shown there. So you can classify depending on the temperature. Tempering processes, you can say that low temperature tempering is around 150 to 250 degrees centigrade. Then medium temperature tempering you can classify as at 350 to 450 degrees centigrade, and high temperature you can classify at 500 to 650 degrees centigrade. So here you can give the classification. Then the same the different temperatures and the different colors okay are there, and for which what kind of tools you are using that, like for suppose you are going for 200 degrees centigrade, then you go for lead tools for brass, then for axis you have 270 degrees centigrade, and for springs you have 300 degrees centigrade. So these are some different colors that are obtained during the tempering process. Now quenching. Now quenching is a process of rapid cooling. You know, rapid cooling. So materials from high temperature to room temperature or even lower. So in steels, quenching results in transformation of austenite to martensite, a non-nuclear process. So during cooling, heat must be extracted at a very fast rate from the steel piece. So this is possible only when a steel piece is allowed to come in contact with some medium which can absorb from the heat steel piece in a strong period. So in the ideal conditions, all the heat absorbed by the medium should be rejected to the surrounding immediately. So their views go for a quenching medium in that. Okay. So quenching medium has a profound effect on the final phase of the material. So quenching medium is directly related to the rate of the cooling of the material. So the widely used quenching media are like water or aqueous solutions or oils. Oils may be mineral, vegetable, or even animal oils, molten salts, and air. These are some quenching media. Now, surface hardening. Now, in many situations, hard and wear resistance surface is required with the toughened core. Now, you are going with the toughened core. So, because of the tough core, the components can withstand load. So, typical applications which include like gear teeth, camshaft, bearing, crank pins, clutch plates, tools, and dies. So, the combination of these properties is achieved by the following methods. Like if you go with the hardening and tempering of the surface layers, they are called as flame hardening and induction hardening, sorry. And changing the composition of surface layers, then you go with the carburizing, nitriding, carburizing, and cyaniding. These are the processes which you go. If you go with the surface layers, then there you have the this process. And if you want to change the composition of surface layers, then you have these kinds of heat treatments. Now for flame hardening, if you go, the flame hardening involves heating the surface of the steel to a temperature above the upper critical point, that is 850 degrees centigrade with an oxyacetylene flame, and then immediately quench the surface with cold water. So this heating transforms the structure of the surface layer to austenite, and then quenching changes to martensite. So how this the upper layer is hardening. Now in induction hardening, it involves placing the steel or the placing the steel component within a coil through which the high frequency is passed. We are talking about after flame hardening, we are going with the induction hardening. So this induction hardening involves placing the steel component within a coil through which the high frequency can be passed. So the current in the oil induce eddy current in the surface layers and the heat the surface layers to the austenite state, and then the surface is immediately quenched. Quenched means cooling down with cold water to transfer the from the austenite to martensite. So the principle of induction hardening is, you can see in the diagram how it is shown. Okay, then carburizing. Now, carburizing is carried out on a steels containing carbon less than 0.2%. It involves increasing the carbon contents on the surface layers up to 0.7 to 0.8%. I repeat, increasing the carbon contents on the surface layers up to 0.7 to 0.8%. So you can see in the diagrams below how this process is shown in the industry. So in this process, the steel is heated in contact with carbon. This is materials from which it absorbs carbon. So this method is mostly used for securing hard and wear resistant surfaces with tough core. Carburizing is used in gears or cams or bearings and fixed plates. Okay. Now nitriding. Nitriding also involves diffusion of nitrogen into the products to form nitrides. So resulting nitride case can be harder than the carburized steel. So this specifically used for alloy steels containing alloying elements like aluminium or chromium or magnesium, aluminium, chromium, and molybdenum, which form stable nitrides. So nitriding consists of if heating the component in a retort of a temperature of around 500 to 600 degrees centigrade. So the ammonia gas is allowed to circulate. At this temperature, the ammonia dissociates by the following reaction like 2NH3 gives 2N plus 3H2. So the atomic nitrogen diffuses into the steel surface and combines with the alloying elements like chromium, molybdenum, vanadium to form hard nitrides. So the depth to which the nitrides are formed in the steel depends on the temperature and the time allowed for the reaction. Okay, it depends upon the temperature and the time allowed for the reaction. So after the nitriding, the job is allowed to cool slowly, and hence there is no quenching involved. The chances of cracking and distortion of the components are less. This is how the nitriding, and then the cyaniding. So similar to carbonitriding, cyaniding is also involved the diffusion of similar to carbon nitriding. Cyaniding is also involved diffusion of carbon and nitrogen into the surface of the steel. It is also called as liquid carbonitriding. So the components are heated to a temperature of about 800 to 900 degrees centigrade in a molten cyanide bath consisting of sodium cyanide, sodium carbonate, and sodium chloride. So after allowing the components in the bath for about 15 to 20 minutes, they are quenched in oil or water. So cyaniding is normally used for low carbon steels and case depth that are less than 0.25 mm. Okay, it is used for low carbon steels and case depths that are usually less than 0.25 mm. So this is the, you can say, limit. So it produces hard and wear resistant surface of this, on the steel because of short time cycles. The process is widely used for machine components subjected to moderate wear and service loads. So items like small gears or screws, nut and bolts are use this kind of process. Now we go with the MCQs for today. Like steels containing this much of carbon are used for carburizing. So what do you think should be the answer? Like I think it should be the answer A, like 0.1 to 0.2% carbon is the answer. And what is the carburizing temperature? It's around 900 to 950 degrees centigrade. Then normalizing is not used for relief stresses by which of the following processes? In which of the processes normalizing is not used for relieving stresses? So the answer is drilling. In drilling, it is not used. So cast iron contains carbon. How much carbon does cast iron contain? So it contains more than 2%. Then normalizing, yes, normalizing is normally used for high carbon steels. Okay, then increase in the increase in the tempering temperature. So what it will do, it will increase toughness. Okay, increase in tempering temperature will increase toughness. Now some of the parameters that use thermal radiations from hot bodies, which depends for black bodies only on temperatures of the body and hence are known as radiation parameters. True or false? So I think it is true. Oh, this is sixth MCQ. Um, seven we did. Eight. The physics of measurement of very high temperatures above 1600 degrees centigrade is called as pyrometry. Okay, a device measuring such high temperatures in pyrometry are called as, we studied earlier, it is called as pyrometers. Okay. Now it is defined as a measure or ease with which hardness is achieved and the ability of a material or of a metal to resist abrasion, indentation, scratching. So what do we call? We called as the hardening. We called it as the hardening. So we've studied about all the MCQs just now, and we studied about radiation parameters. Then you can understand that the heat treatment is a very vast kind of, you can say, a process that is used in the industry. So we should understand each and every process, and whatever is the requirement of the, or you can say whatever is the application of the product, we should apply the heat treatment process according to that. Our purpose is to achieve maximum, you can say application of the product, or achieve a good machinability if required in the product. So we should apply heat process according to that. So if you want to study more in this heat treatment process, you can go with such references that are shown in the screen. These references will give you more knowledge in these topics, and you can also have more diagrams in this. See, if you study more books, that will increase your knowledge in this subject, because you know that uh, when you read books, you try to indulge yourself in the book. So that knowledge gained by you by reading the books will help you to enhance your knowledge, and grow you, you can say mentally and knowledgeably also. So thank you all for now.